Hey there, and welcome to This Explainer. I'm Bizad, your mentor and senior network engineer. Today, we're diving into the absolute foundation of enterprise networking, Ethernet local area networks. You know, whether you're coming from a Network Plus background or you're already getting your hands dirty in the data center, mastering these fundamentals is exactly what separates the good technicians, the guys who just follow troubleshooting guides, from the truly great engineers who actually understand the protocols deep down to fix the really complex problems. So, let's just dive right into this.
Okay, here is our roadmap for today. It's straightforward, but super powerful. First up, the enterprise mystery. Then, we'll look at frames and the postal service. After that, we'll cover hubs, switches, and collisions. And finally, we'll wrap up by solving the duplex mismatch.
So let me take you back to a situation I faced in a major enterprise data center. Users were complaining that this critical application was just painfully slow. I mean, the kind of slow that literally has project managers pacing back and forth outside your cubicle. So I logged in, checked the physical layer. The link was a 100 megabit per second connection. On the command line, the status showed as up, which, means it's physically connected and the line protocol is supposedly functioning perfectly. The green lights, they were happily blinking away. But the application was practically unusable because the link was just constantly dropping packets.
I want you to really think about this for a second. Why would a high-speed Ethernet link, showing a perfectly healthy connected status and blinking a deceitful green light, suddenly just grind to a total halt? Well, to solve this, we can't just guess. We have to step back and understand the foundational theory of how Ethernet actually moves data under the hood.
Which brings us to part 1, frames and the postal service. Let's see how this data actually travels.
The absolute easiest way to visualize the Ethernet data link layer is to compare it to your local postal service. Think about it. When you send a letter, the postal service doesn't care at all about what's written inside, right? It only cares about the physical envelope and the address written on the outside. In networking, Ethernet acts exactly like this local mail delivery system. It takes data from the upper layers, stuffs it inside a digital envelope, a process we officially call Layer 2 encapsulation, and handles the physical delivery from one local device to another over the cables.
But just like a house absolutely needs a unique street address to get its mail, every single network interface card needs a physical address too. And that is your MAC address, or Media Access Control Address. It's a 48-bit or a 6-byte number permanently burned into the hardware. When an Ethernet switch gets our digital envelope, it looks exactly at this destination MAC address to decide where to send the data next. Oh, and here's a quick real-world CCNA trick for you. The first half of that MAC address is the OUI, or Organizationally Unique Identifier. It actually identifies the manufacturer of the network card. So if you ever spot a weird device on your network, looking up the first half of the MAC address is a phenomenal way to figure out exactly what it is.
Now, let's crack open that digital envelope. We call it an Ethernet frame. It consists of a header right at the front, the encapsulated data sitting in the middle, and a trailer at the very end. Inside that trailer is the FCS, the frame check sequence. This is basically a mathematical formula used for error detection. If electrical interference or, say, a bad cable corrupts the frame while it's traveling, the receiving device checks that FCS, realizes the mail is corrupted, and instantly throws it in the trash. Literally. Ethernet is absolutely ruthless. It doesn't politely ask the sender for a replacement, it just silently drops it. Keep that ruthlessness in mind for our mystery.
All right, moving on to part 2, hubs, switches, and collisions. Let's see how the history of networking equipment actually still haunts our data centers today.
So, in the early days of Ethernet, networks were built using hubs. And let's be honest, hubs were not smart. They just blindly repeated electrical signals out to every single port. Because everyone shared the exact same cable bandwidth, devices had to follow a polite wait-your-turn rule called CSMA/CD. They would listen to the wire, and if no one was talking, they'd transmit. But if two devices transmitted at the exact same time, boom, the signals crashed into each other. We call that a collision. When a collision happened, both devices had to stop, wait a random amount of time, and try again. And that random back-off timer, it's incredibly important, because if they both waited exactly 1 second, they just collide again instantly, right? The random timer ensures they stagger their retransmissions.
So the crucial takeaway here is the massive difference between legacy hubs and modern switches. Hubs force devices into half-duplex mode, meaning a device can either send or receive, but never, ever both at the same time because that media is shared. Modern switches, though, they change the game entirely. They provide dedicated point-to-point links.
This allows for full duplex communication, where devices can send and receive data simultaneously without ever having to share the wire with another conversation.
And because those full duplex links on modern enterprise switches are dedicated, totally separate lanes of traffic, collisions should be completely eliminated. I really want to say that with absolute authority because this is a classic trap on CCNA exams. A properly configured switch port operating in full duplex does not even use CSMA-CD anymore. It is completely disabled. The port just sends and receives at will, knowing its lane is 100% clear. Which brings us to part 3, solving the duplex mismatch. Let's take all this theory, head back to the data center, and fix that completely unusable 100 megabit link.
So there I was, standing in the noisy, freezing wiring closet, looking at the blinking lights, and everything seemed totally fine at layer 1. Like I mentioned, the command line told me the interface was up/up. Now, if you just stopped there, you might blame the application team, or maybe the server itself. But as a senior engineer, you know that up/up just means the physical electricity is flowing and the basic protocol is running. It absolutely does not mean the link is actually healthy.
So here are the exact troubleshooting steps we take on the Cisco command line interface when things start getting weird. First, we use the show interfaces status command to verify the connection. Second, we look very closely at the negotiated speed and duplex settings. And third, and honestly most importantly, we use the base show interfaces command to look deep into the error counters.
Well, when I looked at the switch interface counters for our problem link, the standard collision counter was definitely ticking up. But there was a massive red flag staring back at me: excessive late collisions. Yeah, in a normal network, if a collision happens, it happens in the very first 64 bytes of the frame. Why 64 bytes? Because 64 bytes is the minimum Ethernet frame size, which directly relates to the maximum time it takes for an electrical signal to propagate across the wire and for a device to sense a collision. So, if a collision happens after 64 bytes are already transmitted, we call it a late collision. And in a modern switch network, late collisions almost always point to one specific disastrous configuration error.
The culprit? A duplex mismatch. This happens when the device on one end of the cable operates in full duplex, while the switch port on the other end is stuck operating in half duplex. This perfectly illustrates our exact mystery. The server, let's call it PC1 here, was manually set to full duplex by some previous technician. It thought it had a dedicated lane, so it transmitted data whenever it wanted, completely ignoring those polite CSMA-CD rules. The switch port, however, experienced a super common real-world issue: auto-negotiation failure. Because it couldn't negotiate with that manually configured server, it fell back to the default for 100 megabits, which is half duplex. So the switch port was being polite, listening to the wire, trying to take turns. But when the server shouted over at mid-sentence, the switch recorded a late collision. And because of that ruthless FCS error detection we talked about earlier, the switch dropped the corrupted frame entirely. The link was physically up, for sure, but logically, it was tearing itself apart.
Once I fixed the configuration to ensure both sides were correctly locked to full duplex, the collision stopped instantly, and the application speed went right back to normal. And this brings us to your major mentorship takeaway for today. A working link isn't always a healthy link. Never ever trust the green light. You always have to verify your speed and duplex settings and aggressively check those interface counters.
So, I'm going to leave you with this to really think about as you head back to your own networks. Are your working links secretly dropping packets right now? Go log into your switches, check your error counters, and make absolutely sure you don't have a duplex mismatch hiding in plain sight. Keep learning, keep digging deeper than the surface level, and I will see you in the next explainer.